Hello and greetings to everyone at Deep Tech. This is Steve Chao from Turing Industries. We're going to talk about quantum computers and neuromorphic computing today. Quantum computers seems a little far-fetched. However, they're extremely promising. Back in 2019, Google claimed to have achieved quantum supremacy. That's a quantum computer with 53 qubits. What are qubits? Conventional computers uses bits, that's ones and zeros. Quantum computer uses qubits. It's able to perform two calculations at the same time with one qubit. With 2 qubits, the quantum computer is able to perform 4 calculations at the same time. That's 2 to the power of 2. A 53 qubits quantum computer may perform 2 to the power of 53 calculations simultaneously. Now, if suppose there's a quantum computer with 300 qubits, that means it's able to perform 2 to the power of 300 calculations at the same time. Now, that number is more than the number of atoms in the visible universe. So, as powerful as it seems, it comes with a little hurdle. For quantum computers to work, it needs to be cooled down to minus 237 degrees Celsius, close to absolute zero. That's not exactly practical for day-to-day usage. Therefore, quantum computers are used specifically for special tasks. It isn't built for general computing. Now, neuromorphic computing is a much better candidate for next-generation computation. The term was first conceived by Professor Carver Mead back in the 80s. It is describing the computation mimicking the human brain. Over the last decade, a number of companies and institutions have been working on neuromorphic computing. Take IBM as an example, the IBM TrueNorth chip. It's the first neuromorphic chip in the world that takes on the non-von Neumann architecture. The TrueNorth chip has 4,096 cores. Each core contains 256 neurons. We're talking about 1 million neurons and over 250 million synapses. Now, this is a relatively new concept of computing. As I have just mentioned neuron, let's touch upon the biological aspect of this topic, the human brain. A typical human brain contains in between 86 to 87 billion neurons and 10 to the 15 power of synapse. Inside each neuron, we have the cell body, or soma. Surrounding the soma, we have the dendrites. Branching off the soma, we have the axon. At the end of the axon, we have the axon terminal. Now, think of the dendrites as the antenna for receiving signals, and think of the axon terminals as the antenna for sending signals. The neurons within the human brain send signals by firing spikes at each other. It only fires spikes when the membrane potential reaches a certain value. Now, the spike doesn't necessarily fire at each propagation cycle. This is why when we perform a task, a computational task in our brain, we only consume a tiny fraction of our entire neuron count. This is the reason why the human brain is extremely power efficient. We consume 20 watts of power, and we're capable of achieving 1 exaflops. And let's put this into perspective. The world's fastest supercomputer, the IBM Summit, consumes 13 megawatts of power, and is capable of 200 petaflops. The human brain consumes 20 watts of power and capable of 1 exaflops. That's 5 times the computational capacity of the IBM Summit. Neuromorphic computers, which uses neuromorphic computing, are directly modeled after the human brain. It uses a special artificial neural network methodology called spiking neural networks, or SNN. This is not to be confused with software-based algorithms such as convolutional neural networks, recurrent neural networks, or generative adversarial networks. Neuromorphic chips, which powers neuromorphic computers, may not replace conventional computational chips such as CPU, GPU, or application-specific ICs. However, neuromorphic computers has the ability to add to the existing computers that performs deep learning for artificial intelligence. From IBM TrueNorth to Intel Loihi to Manchester University's Spinnaker machine, every company or institution is working on a unique solution for neuromorphic computing chips. We at Turing Industries, we're also working on a special type of neuromorphic chip based on non-volatile memory chips. Non-volatile memory chips such as RAM or phase change memory are special because when the power is down, the data stays. Unlike random access memory such as DRAM, the data is lost after the power is gone. This is particularly important for next generation artificial intelligence research, that is, artificial general intelligence. In terms of AGI, we first need to explore the possibility of artificial consciousness. Now, there are two aspects to consciousness. First, the unconscious. It's intuitive, it's fast, it's non-linguistic, it's habitual. However, it deals only with implicit type of knowledge. Whereas conscious, it's linguistic, it's algorithmic, it deals with reasoning and planning, an explicit type of knowledge. The non-volatile memory chip-based neuromorphic computing chips has the potential to tackle the reasoning and the planning of the conscious mind, which is important as a milestone for the next generation neuromorphic computing research. So, what does it all mean for us? What does it mean for iGaming in particular? Suppose we're able to conceive that kind of hardware and we're able to perform research on artificial consciousness. That means we'll be able to zero into the attention-based artificial intelligence without having to gone through millions and trillions of data. We can just focus on the kind of data that really matters to us, like how we humans see things. We receive information and data at an astronomical rate on a daily basis. However, we have the ability to focus our attention on the ones that matters to us, and machines lack that kind of ability. In other words, if machines have that kind of ability, that means it will be able to create an intuitive experience for gamers online, and gamers will be able to enjoy and spend more time interacting with the machine as if there's a real person on the other side of the screen or the table. I've enjoyed sharing such knowledge with you, and maybe one day machines will be able to develop self-consciousness and share their knowledge with us. I don't think we have to worry about technological singularity. In the interim, what we should do is enjoy iGaming. Thank you so much. Thank you, Deep Tech.
Wow, Steve, that was some presentation. I'll be honest with you, some of that went whoosh, right over my head. The technology that you talk about is extremely interesting. There's a couple of things that I've picked up on that I wasn't very much aware of. One, that quantum computing is not only in existence, but it's functional and being used. I genuinely thought that was theoretical so far. And there's elements of that I'd really like to discuss with you. And secondly, this completely new terminology in neuromorphic computing, where it's highly interesting to see how we are mapping the human brain and how we are mapping neurons. I have questions in terms of whether it's biological, technical, nanotechnology, what's going on there. So there's two key areas rolling on from the previous conversations I've just had, one being with an AI panel, and quite literally we've closed the topic on the amount of computing and processing power that we currently have in the technology today, where that is headed. And the second conversation that was just held by Jason Farrugia, CTO of MGA, which is a fantastic panel on cybersecurity. and on encryption, on safeguarding the customer data. So those are the two core verticals I'd like to explore when we talk about the new computing capabilities. With me, Steve. Hi, welcome.
Thank you.
Great. There you are. How are you? Are you good? Can you hear me well?
Thanks a lot.
I'm losing you, Steve. Can you please repeat that?
I can hear you fine. Thanks very much.
There's a slight delay. Right. So, looking at quantum computing first and foremost, right? The amount of processing power that you've just described there seems staggering. And as somebody that has been on the receiving end of brute force attacks and DDoS attacks when I ran my casino operations, and has been on receiving end on the file locker hacks and various intrusive elements. One thing that would concern me is what happens with cryptography, especially, I'm not talking military grade cryptography, I'm talking about standard e-commerce, the usual 128 and 256-bit encryptions when they are confronted with machinery of this particular capacity. I mean, are we going to start seeing quantum computers in the hands of relatively rich, private entities, which may not necessarily have the necessary regulation and safeguards, that NSA would have, or someone as big as Google? Where does quantum computing sit right now? I have a very similar question for neuromorphic computing as well, because obviously, as you've stated, the processing power, they seem to be competitive to one another. What is your take on that?
Okay, so as I talked about quantum supremacy that was achieved and claimed by Google last year, but we should really note that the current quantum computer is at 53 qubits. Now, to break a standard encryption technology such as RSA, you probably need over 10,000 qubits to crack the RSA. So not to mention that there's AES 256, and most of the seed private keys are being selected by the ECC algorithm. So I think this is still far out in terms of quantum computing being able to crack the cybersecurity. So I wouldn't worry too much about it.
You're saying we're safe, we're good.
Oh, absolutely, yes.
Yeah, very good. Okay, I mean, that was one question. I mean, the second part of the question was neuromorphic computing. So I understand, I mean, when I listen to your presentation, I imagine the environment in which I or any entity is supposed to bring the temperature down to the absolute zero and so on. I can't imagine this rolling out in any form of commercial scale at any point in the near future. But when you talk about neuromorphic chip, you see that really threw me off. When you mention neuron, one of the things that kept bringing up, neuron is a biological element, right? I've watched the latest technology trying to store data on DNA, I think quite successfully. When you talk about the technology that produces this chip and its capacity, what are we looking at here? Is this nanotechnology? Is this a new form of wiring, atom chips? I'm completely at a loss at what we are looking here in terms of what's coming out.
So neuromorphic chips are relatively new. Now, neuromorphic chips, it's largely based on the heterogeneous architecture. As opposed to quantum computer, the neuromorphic chip nowadays utilizes both the logic side of things, meaning the CPU type of capability for deep training. Mm-hmm. However, at the same time, it also drills into the reasoning and the planning aspect of the chip. So it's got the right brain of computation. It also has the left brain built into it. And different companies are working towards a solution to make it commercial at the moment.
So one thing that confused me was, at one point in time, you've mentioned its ability to store data in its off state. Now, that contradicts my understanding of processing itself, right? For me, conventional processing processes data that's stored in a database, right? When you look at the chip, are we looking at ability to store information as well and process it on that chip?
Yeah, that's called in-memory computation. So that's a topic that many institutions are trying to solve, the traditional von Neumann bottleneck, meaning when you have the processing and the data going back and forth, it you loses data and it consumes a lot of power. Now with in-memory computing,
just understanding that the verticals rolling off from the previous AI conversation, the verticals that we're embarking on, it's almost scary. Okay, so if I understood this right, what's rolling on in very near future, and correct me if I'm wrong, quite frankly, exists as of today. IBM has developed that chip. That chip is currently in use, right? What is happening is a high enough degree of reasoning and computation capacity of a human brain stored in a chip, right? If I remember right from your presentation, you've explained the computational capacity of a human brain, and if I heard you right, comparatively, we're looking at a chip that can do 10-20% of that already as a single chip. Did I understand that right, or did I misunderstand that statement?
You implied it correctly, but I think we're still quite a few years off from mimicking the entire human brain's computation. At this moment, the only institution which have mimicked 1% of the human brain is Manchester University's Spinnaker project.
So 1% of the human brain, yeah?
Right now, which is like the equivalent of a mouse.
Yeah, okay, fair enough. But when I was looking at statistics, I said, did I hear this right? I wasn't 100% sure. I want to clarify that topic. So a couple of things that I extracted from this conversation that are very interesting to me is one, in-memory computing and the high ability for in-memory computing ties along incredibly well with real-time responsive design. So when we're looking at AI architectures, which need to respond to events, external events in real time, this is quite frankly the next frontier, I imagine. This is where we're headed.
Absolutely.
I mean, absolutely. I mean, I'm thinking iRobot here. I've gone there. but from the perspective of the use for the industry, I mean, this goes well beyond the gaming industry itself. But for the use from the industry, one of the closing conversations of the AI aspect was that we are inversing the learning mechanism. So we were talking about machine learning from the aspect of giving it certain variables and giving it certain information points and teaching it the basics of how to structure those information points to extract reasoned data, as opposed to allowing a machine an unfettered access to a data lake, to a pool of data, especially event-driven, allowing it to stream through those events to find common denominating patterns and to reach conclusions. And that inverse approach to AI for me was sort of a long ways away, simply because I couldn't imagine a scenario where our processing capabilities and our database capabilities can sort of bring any realism to that aspect. But with what you're saying here now, we're a cornerstone away.
Well, actually, very close to achieving the sort of artificial general intelligence. So what you have just described is unstructured data or unsupervised training. Unsupervised training is particularly suitable for neuromorphic computing, especially in the realm of in-memory computing. I think we're only about 2-3 years off. far quicker than quantum computers.
Incredible. So commercially, is this anywhere close to being commercially available? I mean, how does this look like? Company wanting to embark on this. How does the availability of such technology even look like at this day and age right now?
Okay, I'm not trying to do a commercial on our company, but in about 2 to maximum 3 years, we will be able to offer this commercially. Most of the neuromorphic chips that you know out there, they are mainly for academic purposes. The IBM TrueNorth was specially built for DARPA, for the American Defense Ministry. Yes. And Intel Loihi is still in the academic research stage. But what we're working on is based on nonvolatile memory, and this type of in-memory computing have already been sold to many clients already. Not in the realm of neuromorphic, but in the realm of memory, volatile memory itself. So we're about 2 to maximum 3 years out, and we're working exactly to bring it commercially available.
That's incredible. So 2-3 years from now, the world is going to change again. That's how it sounds.
Yeah.
Wow, amazing.
That's right.
We're out of time. Steve, thank you so much for that amazing presentation. Thank you for this conversation.
Thank you, Igor. Thank you,
Wonderful.
Deep Tech.
Have a lovely day.
See ya. Goodbye.